Hello. Right, let's have a look at work solution 7. And so we're doing the shear graphs, shear force graphs and the bending moment graphs. So our problem has been set up for us in the sense that we've already got the supports here and here. We've applied these loads, located them, and so I know where the end of the bar is, A, B, C, D and E. What else can I say? That's about it really. So everything there has been set up. What would be good maybe to do, the only thing you might want to left doing on this diagram is you might want to be looking at the actual distances. So you might want to like start summing things up. So that's 4 meters to go from there to there, and that's going to be 7 meters from there to there. Okay, because what I'm interested in is looking at these positions when I hit them. So I'm going to hit that at 1 meter, I'm going to hit that at 4 meters, I'm going to hit that at 7 meters. I'm going to use that information later. So let's crack on. So we're going to construct a shear force diagram and a bending moment diagram from this beam problem. So first, what we're going to do to make this diagram is do it slightly differently to how I did it in the lecture. So in the lecture I took the approach of let's first find my shear force diagram and then move on and then find my bending moment diagram. Okay. The approach we're using in this work solution is slightly different in the sense that we're going to do both of these things at the same time, in conjunction this time, and we're going to go through section by section. So we're going to go to look for a section where we've got something interesting happening, and we're going to stop there. So we can define this as a section A to B. Okay, so I can see nothing's happening between A and B. This will be my next section, B to C, and this will be my next section, C to D, and that will be my final section there, D to E. So we're just going to consider being in this section, and what I'm going to do here is take an imaginary cut, I call that my XX line, and then look left of me. So I'm in section AB, and we're there, we've got this XX line there, and then we look left. So the first thing we're going to decide is how far is it to get from there. Well, that's almost by definition, as it were, is x. So we're an x distance away. What can we see left of us? Well, not much, to be honest. The shear force experienced by this section is the sum of the external forces to the left of xx. And we're going to use the UE sign convention for defining if the value of force is going to be positive or negative. So the UE convention is if it's positive, if it's going up it's going to be positive, and if it's going down it's going to be negative. So for the shear force we're going to use the symbol Q. Note that a lot of other textbooks and MD Solids, they use the symbol V for shear. So what can I see left of me? Well, nothing. So the answer is going to be 0 kilonewtons. What about the bending moment? The bending moment experienced by this section is the sum of all external moments to the left of XX. So I'm imagining we've got a pivot here, and we're looking for any moments left of me. Can I see any forces left of me that might cause a turning? The pivot point for consideration is the XX, not at A. So it's at this point here that we're looking for moments. Since there are no forces there, no moments can be there. And the symbol we're going to use in this case is going to be M, XX. So we're going to have 0 kilonewton meters left of us. So that sorts out my plot for both Q and M, and I could start, if I was like doing this exam, I could start plotting them away now. So I could start going, well, my Q is going to be like this. For the first meter, I'm going to get 0. Very easy to forget doing your first meter if you've got 0 left to you. And my M for the first meter will be 0. So I could start plotting them. Now let's go to BC. Okay, BC. Now we're a bit more interested in the region here. So we've shifted our line into this BC region, and we're looking for X. So what is the distance to get back to A, the start? Well, that's still going to be X. What is the distance to get back now to B? Well, we're going to have to measure that. So I can do that in the sense that I know that it's 1 meter to get from here to here. It's X to get to my XX line. So this distance here will be X take away 1. Okay, and that's why in my original diagram it's good to label up where these points are, these X equals 1, X equals 4, because we're going to be putting them into our bracket here. So X take away 1 will be this distance. So what's the shear force experienced by this section? First of all, I don't need the distance for shear force, but I do need it for the bending moment diagram. So just looking left of me, all I can see is this 20 kilonewtons. It's going downwards, so we're going to put that into negative. So that will give me my Q value, what I've got. And when you find your Q value and you're going through the sections, you keep these things separate, and you do that for a reason that you can see later. Now we do have some bending moment. We do have a force left to us, and it is going to cause a turn-in there. So we're going to get an anti-clockwise turn-in. And now you can see the advantage of doing the Q after the M and sweeping through the beam here, because when you introduce a new Q term, then you can introduce a new M term. So we can just drop down from our previous equation there for Q, which is minus 20. I can drop the minus 20 down, and then I can multiply it by the distance, and that's all I have to do then for the bending moment diagram. That seems a bit too easy. So that's all I'm doing. I'm going to use this. That's part of the UE convention. Makes it nice and easy. So we just take our minus 20 value, drop it down, then multiply it by the distance from the pivot there, which is x minus 1. So that's going to be true for when we're between B and C, which happens to be between 1 and 4. The other thing that you might want to do, in particular for M, is you might want to go along and then start, when you got these nice straight lines, start saying, well, what does M equal when we get when we're at x equals 1? So let's plot that. So x equals 1 or m equals 0. Yeah, I know that. And what does m equal when x equals 4? So I put 4 in there, and that gives me minus 60. So if we were doing our plot as we we're going along, so this is my Q, this is my M. My first meter is just flat, and then from 1 to 4, well, Q just drops down, minus 20, and so I could put minus 20 there. Here, when we get to 4, we should have m equals minus 60. It doesn't have to be the same scale. So minus 60. Okay. So you can see the advantage of like putting in your values of what is m when I'm at this point and what's m at this point here. So I can start plotting this graph. Whoops. And so that's what we've done here. So we've put in x equals 1, so I can plot that later, and x equals 4, so I can plot that later. Now let's move on to C to D. So we're now in this region. Now I've got something interesting here. You've got two approaches that you could deal with this. You could either combine this into a total force, no reason not to, or you could keep them separate, no reason not to. So using the shear force, we're gonna adopt the approach of keeping these separate. So I can see that I've got a minus 20 going downwards, a minus 40 going downwards, and then I've got an 85 coming upwards. And I'm going to keep these separate. So these are my working bits of data there. That's going to help me with my M graph when I come to it later. But I'm also going to sum up the result for when I want to now do my plot for my Q graph. So remember we had initially flat line in, and then we stepped down in minus 20, and then we've done 4 meters, and then we're going to shoot up 25. So you can use that value there on your graph and plot it. Let's come to the bending moment diagram. So this is the advantage of using the Q values and having them all separate, and just keeping a current tally for your graph plotting next to it. So the minus 20 comes down, the minus 40 comes down, the plus 85 comes down, and now the next thing we do is look for the distances from the pivot back to those particular values. So the minus 20, well, that has a distance of x, take away 1, and to get from here to here, that's going to have a value of x, take away 4. So open a bracket, x take away 4, x take away 4, and then that's my bending moment diagram. And the next thing I want to do is put in the values where C starts and where D finishes. So that gives me equations that are valid between 4 meters and 7 meters. So I'm going to put m equals 4 into this equation and m equals 7. You might notice that actually we only really need to have the last value, because from our previous section we would have known what m equals up to this point, and it's a continuous line. So when I substitute in m equals 4, I get minus 60 as I previously found. Always useful, I suppose, as a check. And then when I am at x equals 7, then I'm getting m equals 15. What about when I'm in the region D to E? Well, now I can see I've got this force going downwards, this one going downwards, this one going downwards, and that one going up. So for my shear force diagram, I should have four forces: minus 20 going downwards, minus 40 going downwards, plus 85. Keep them nice in order, so we're going to keep them in order, and then minus 30 going downwards. Let's sum them all up for our graph. So we're going to get minus 5 there, and then we're going to keep these set of data, and we're going to plump it down into my M graph. So for the bending moment graph, we'll take the minus 20. How far is it? Notice these things don't change as we go from one section to another section. And then we've got x minus 1 for the first one, so that's that distance. X minus 4, so that's that distance. And what's the distance here? Well, it's a total of 7, so it's going to be x minus 7 for the last number there, and that's going downwards. So straightforward. And that gives us a valid range for values of 7 to 10. Again, it might be nice finding out what m equals 7. You don't really need to, you've previously found it. And then substituting in what the value of m is at 10. So when I substitute in the value of x equals 7, I get the previous result of 15. And when I substitute the value of x equals 10, this is a check really, I'm going to get the value of 0. And what we're saying there is, the other thing we can do, of course, is look at what is the last reaction that we get, and the last reaction we should have should be plus 5 kilonewtons when we look at all the beam. So that would then tell us that when I sum up all my forces in the y direction, that they equal 0, and when I get to the end of the beam and sum up my turning moments, they will equal 0. So when you introduce the final bit, so that's that upward force there, you can see that your forces will sum up to be 0. That won't create, we're now at the end of the beam, so that won't create any turning moment, so that doesn't affect my my EMA graph. But you can use that then to check that your shear forces have summed to 0. Yes, they have. And job done. We're all in the dark.